Okay, hello, hello, hello. Good evening, one and all. Thank you for rolling in. We are going to be talking about the African Millimetre Telescope this evening, and I hope you're all at the right place and interested in that. Okay, so I'm John Pallett. I'm an environmental consultant, and this meeting is part environmental assessment business and part kind of publicity and information about the AMT, the African Millimetre Telescope. So I'll be in charge of things, and then I'll hand over to Mark, and then once we've had a nice background to the science and why we're doing this at all, then we'll go back to the EIA aspects. Okay, so as I said, I'm John. I'm an environmental consultant for Resilient Environmental Solutions, a small EIA company in Namibia. My colleague is Henriette Potgieter, who is taking notes there at the back. And let's just also hand the microphone to Mark for you to introduce yourself. Just briefly.
Yes, I'm Mark Kleinwald. I'm project director of the African Millimetre Telescope and director of a lab in the Netherlands who builds instrumentation for astronomy. Maybe I want to give the mic to my colleague.
Okay. Yes, hello everyone. I'm Michael Bacchus. I'm a professor here at UNAM in physics and leading the AMT project from the UNAM and Namibian side.
Okay, thank you. And also on the team we have Zandre Duvenage, who's giving away from the back. So Zandre is the kind of PRO type person for this project. So onwards. Hello. What do I do here, Mark? Oh, and hello to the people online. I can't see, actually, we've got a few people there. So good afternoon to you all, and we'll try and, okay, there we are. We'll try and keep attention to if anybody raises their hand on that thing. Okay, so we've done the introductions, and okay, so just briefly, what we're going to be doing this evening. There is a register. Please do fill in the attendance register. That's an important part of the EIA process, just making note of who has actually come to these meetings, and everything will be minuted and noted. We'll go through just briefly about the environmental assessment process. That'll be done by me. Mark will give some scientific background to the project. Then I'll go into the kind of nitty-gritty of what's actually going to happen on the ground if we haven't heard enough of it already. And then we go into a short discussion about impacts and what kind of concerns anybody might want to raise, and we can tell you what we've heard already in the process. And if there are any concerns, this is the opportunity to raise them, and then how we proceed from there. So it's fairly straightforward. We expect to be busy for an hour, but more than that maybe, we'll see. Okay, so in an EIA, Environmental Impact Assessment, which is also the same as ESIA, Environmental and Social Impact Assessment, this is obviously a project which does trigger the need for an environmental clearance certificate. It's not a tiny thing, so it does need that, and that means it's got to be registered with the Ministry of Environment. And we go through a scoping phase, which is where we are now, to kind of understand what is actually going to happen in the project, what are the developments which are intended, and how's that all going to work. And we start thinking about, well, what are the impacts? Is there going to be a shortage of water for construction? Are there going to be difficulties with the construction camp? Those kind of issues, people can raise them. This is the time to do that. Okay, so this is the scoping phase. It's also the time where we can do preliminary studies. So I'm doing a fairly short and sweet botanical study, so we don't tread on any endangered plants or anything on the actual site. Also out of necessity, we need to do an archaeological survey, so to make sure there's no archaeological stuff in the footprint of the site. So those things are happening now. If it's a really big project, it goes into a main environmental assessment. But this project is just really a construction project. There's nothing much more to it than that actually on the ground, so we don't think we're going to have to go through any specialist studies and a major assessment. So essentially we hand the scoping report, we submit that to the Environmental Commissioner in the Ministry of Environment, and hopefully that gets an approval and an environmental clearance certificate is issued, and then only after that can construction on the ground begin. Okay, so that's kind of where we are in the environmental assessment process. And when I press that, it doesn't want to do anything. So it keeps on wanting to go quiet. Okay, so you've arrived at the right stage, Mark. Okay. Just really, why are we building this telescope at all? What's the fuss? Why are we doing these things? Mark's going to tell us everything there. Everything.
Thank you, John. Let me quickly, I need to change to something else. I hope it's now visible online as well. Yes? Okay, cool. Well, thanks, John, for the introduction, and I'm happy to see everyone here tonight, familiar faces and some not familiar faces. My task is to explain to you a little bit what the fun thing is about this project, and give you a little bit of background. And some of those things you may have heard already, and some will be new to you. We're talking about, in the end, our main goal is to make that image, or to make that even better. That's the image of the black hole. And I'm showing you a view of our galaxy, our own Milky Way, as we move inside into that Milky Way. And these are actual images, so this is not a simulation. We're zooming into the center of our own galaxy, and this is where we made that first image. So the telescope we're building here in Namibia is to make, the goal of that telescope is to make that image that you just saw, this image, even better. And my story today is a little bit about how we are going to do that. So a little bit about why, and how do we see a black hole, what is a black hole, and also how do we make an image like this? How does it actually work? And then I'm giving you a little bit of an overview of where we are in the project currently. I think, yeah. So I'm talking about an image, but in fact we already have two images. So we have the image that I just showed you of our own galaxy, Sagittarius A star. But before that, the actual first image that we made of a black hole is of a black hole in another galaxy. And that black hole is 1,000 times bigger and also 1,000 times further away. So it looks to have the same, appears to have the same angular size in the sky. And that's why we could image this also with our telescope. But I'll come back to that later. But these are the actual two images that are there. Now, the AMT will mostly focus on observations of our own galaxy. And I'll explain later why. This is fundamental science, what we're doing. Making those two images is one of the biggest breakthroughs in science for a long time. And it was on many of the newspapers. So when you do a science project and you are able to get this kind of publicity, then you're really doing something fundamental, right? But I have to explain to you why that is as well, right? It's not, you cannot always trust all what the journalists are telling you, right? We have to have proof for that. But at least this shows you that people believed it. Okay, black holes. We made this little animation for a podcast series or a documentary series that I have in the Netherlands. So some of these words may be in Dutch, but you'll understand it. When I explain black holes to kids at school, I'm just telling them the black hole is so massive that you cannot escape from it. So if you move close to it in your spaceship, you can, if you're not too close, you can just move around it like with any other object. But if you come too close and you go over the edge, over the event horizon, you fall in and you disappear and you never come back. Now, explaining that to kids, I usually use rockets because rockets are cool. And you just say, okay, why is a black hole black? And why is everything, falling back into it? You could explain it by the principle of escape velocity, which is basically saying you need a certain kind of speed or a certain kind of energy to leave the Earth, right? That's the escape velocity that a rocket needs. And the escape velocity on Earth is about 11.2 kilometers per second. On the Sun, it's higher. On the black hole, the escape velocity is 300,000 kilometers per second, or faster. It's just faster than the speed of light, right? So basically, the escape velocity, or the energy you need to escape from a black hole, is larger. The speed is larger than the speed of light, and that's not possible. It's not allowed. So basically, nothing can escape from that. So that's usually how we explain black holes. Now, there's another way of explaining black holes, and this is really talking about simple gravity. And there's another way that Einstein explained, and then he really uses what we call the curvature of space and time. So we're describing gravity, the fact that the apple falls from the tree to the ground, not by saying that the apple and the Earth are attracted to each other, but by saying that the Earth is curving the space and time in such a way that the apple has to move over that line, because that's the simplest way for his movement to be. And that's another way of describing it. And in that picture, having a curved space-time, the black hole makes the biggest curve. It makes a hole in space and time, right? And it can even drag it around, because black holes can rotate. Now, if that's really the case, I'm talking to you about a black hole that doesn't emit any light. So what the hell am I showing you all those pictures in the newspaper, right? There's light coming from the black hole. How do we see it? This is the first drawing. It's a computer-guided image. It's drawn by hand of how light is bent around the black hole. Because people knew black holes do not exist alone. They're not solitary, right? There's always material around it. There could be stars around it, many stars. If it's a big black hole, like the black holes in the center of our galaxy, or if it's a small black hole, there could be another star around it. And material falls into that black hole. And that material gives off light. And that light you can see before it goes over the event horizon, right? I showed you that movie with the little rocket. If you move outside the event horizon, you can escape. So light can escape there as well. Only when the material that's emitting the light falls in the event horizon, crosses the border, you cannot see it anymore. But light could be coming from just outside the black hole. And this is the first ever of those images that they made. And then there was a Hollywood movie that tried to do the same thing. Why is it not moving? You see, John, I have the same problem. Maybe now it works. Yes. So in Interstellar, in the movie Interstellar, they actually talk to scientists, how does light bending around the black hole work? And if you do that correctly, and you use computer simulations, it looks a bit like this. Now, this is the Hollywood version. Okay, there's more light going out. This is the, this is actually the frame dragging of the rotating black hole. So what's happened if you have a black hole that doesn't rotate, it stands still, you have a hole in your space-time, right? In this case, the black hole is rotating. What it's doing is it's dragging space-time around it, meaning that light can go actually following those black lines. Light can go in all kinds of crazy directions. And if you do those calculations correctly, then you get something like this, which is, you see the black hole here in the center, and you can see that even light can get trapped around the black hole, but it can also go in all kinds of crazy directions. There could actually be light coming from one side, going around the black hole and going back to the other side. In fact, what I explain to kids always, when you're standing on the imaginary surface of the black hole and you look in one direction, you can see the back of your head, because your light ray that is coming from the back of your head will go all around the black hole and come into your eye. That's what's happening here, in what we call the photon sphere. But around the black hole, light can come from all kinds of weird directions. If you would be moving in the rocket, again, the rocket, I use it a lot, and you move towards the black hole, then what will happen to you is you will get drawn in and spaghettified because gravity is like really, really strong. But before all that happens, what you will see is that there's all kinds of light sources that you would normally not see, all of a sudden become visible in this area just around the black hole. So if you go closer and closer and closer, you will start to see most of the universe that's behind you, that normally the light doesn't come there, but it goes there around the black hole and comes into your eye. So there will be a region around the black hole where you see the whole of the universe. So this is, you know, these kind of simulations we can do, we can make, we can see how light is bent around the black hole, and also what kind of image we would get from that. So we're looking at that. But how do we know that, you know, black holes exist? How do we know there's a black hole in the center of our galaxy? This is our galaxy, right? I thought we start with a familiar image. This one is even, I think, taken on one of our team members on one of our trips. So here you see the dust clouds and the stars in our galaxy. Most of the stars we see in the night are just stars in our own neighborhood, and we are in this flat pancake that looks like this if you see it from above. We cannot make this image, right, because we're inside this thing. This is a flat pancake, and we're sitting at 2/3 from the center at 27,000 light years. 1 light year is 1.5 billion kilometers. So this is the distance from us to the center of the black hole, and we're sitting inside this pancake, and if you look into one direction, let's say we look into this direction, you see some stars. Or when you look in that direction, out of the plane, you see stars, right? So in the previous image, those are all the stars that you see. If you look into this direction, or that direction, inside the pancake, you see that dust band, right? So this is the Milky Way. We're part of that. So the thing you see on the sky is not a projection of something else. It's what we are part of. You are part of that thing, right? You're inside that galaxy. Now, a galaxy like this, and this is the fun part, I'm going to ask Zandre, how many stars are there in the galaxy, Zandre? Yeah. So we always have this debate, and there's more a discussion about billion and million and Dutch versus English, but 400 billion stars. I looked it up again today, because my estimate of the amount of these kind of galaxies in our universe always was also 200 billion. Now, I just looked it up today, and they said, no, it's more, it's 2 trillion, 2,000 billion, right? And that's the amount of galaxies in our universe, and then each of these galaxies has 100 to 200 billion stars, and we're just one of them, right? So if this, I'm going to show you something, and then I'm going to do that little thing. Yes, it's working. This is another galaxy. It's a pretty lousy picture, but if we zoom out, you see a part of the sky which we call the Virgo cluster. This has about a couple of thousands of other galaxies. If you look closely, you will see galaxy. This was the galaxy that we were looking at. So this is similar like our own Milky Way. But in this little field, this is our neighborhood. Our galaxy is part of this cluster of galaxies. You see a couple of thousands of galaxies, all with hundreds of billions of stars. So if the universe is this whole, then this little grain of dust on my finger is our own galaxy. Just to give you an idea. I'm not saying it's absolutely correct, but give you a ballpark idea. How do we know that these galaxies have black holes in them? This is a galaxy that we've observed with the Hubble Space Telescope that you probably heard of. Here you go. And it's 1,000 times heavier, so it has 1,000 times more stars than our own galaxy. And when you look at this in optical light, it looks like this, and then when you look at it in radio, it looks like this. Like something is blowing away from this galaxy over 1.5 million light years. So our own galaxy was 100,000 light years across. This is 1.5 million light years. And the light year is the distance light travels in 1 year, 9.5 billion kilometers. So these are big numbers, right? We expect that in this galaxy, there's a 2.5 billion solar mass black hole. That is a black hole with a mass of 2.5 billion times the mass of our sun, sitting in this galaxy in the middle. And we know that galaxies like this, which have, we estimated, these black holes in the center, they give these enormous jets off. So for us, these kind of jets are signatures for black holes. That's one of the signatures that we have. The other signature came from this work that got the Nobel Prize. This is again a zoom in into our own galaxy. You recognize the Milky Way. Now we're moving in, and all these images are real. At some point you go into a simulation, but you will see when that happens. But this is all real observations taken by different telescopes, zooming in to closer and closer to the center of our own galaxy, just to see what's happening there. Because we want to make that image, because we know that stars in the center of our galaxy fall into the black hole. We know that. We think we knew that. But this work showed that for the first time. It showed that these stars, these images are taken with the Very Large Telescope in Chile, are moving around something, a central object that is not visible. A central object that, based on these measurements, is about 4 million times the mass of our sun, but confined to a region which is just, if you put it at the center of our solar system, at the place of the sun, just comes to the orbit of Mercury. Now this is the animation, of course, this is not real, but here we tracked all the orbits of all the stars. And based on these calculations, we know that here there must be a black hole. Now this we can do in our own galaxy, but not in other galaxies, right? In other galaxies they are so far away that we cannot see the individual stars. We can only see that in our own Milky Way. Are you still there? Cool. Just checking. So we tried to make the images of black holes, and you saw them in the beginning already. We succeeded already in that, right? So that's not why we're here. We want to make it better. That's why we want to build a telescope in Namibia. But the reason why we do that is to do science, not to only make pretty pictures. This is the science part. So what you see here are the best animations, simulations, I have to say, not animation, simulations, based on all the complicated physics. So everything that Einstein told us, everything that we know about gas theory, magnetohydrodynamics, relativity, Einstein, it's all in here, right? And what we have done here is we created a black hole and we dumped matter onto it. And then we let the simulation go and we see how it looks like. And this is what we get. These are movies, and you can see our models even show that there's a jet outflow, like in that image that I showed you before. So these are movies of how matter flows around the black hole and how, if we make the image with our telescope, how it would look like. So we're basically predicting what the image would look like. Now, we can make 1,000 of these kind of simulations every time with different conditions. We can change the conditions. We can change the spin of the black hole. We can change the mass of the black hole. We can change something about how matter interacts with each other, how important relativity is, or how important magnetohydrodynamics is. We can change a lot of boundary conditions. So we can change even the kind of physics that we have, right? Because the black hole, the way that we describe black holes, there's no physics yet for that. We're still formulating that theory. That is a theory that describes everything that is big, gravity, and everything that's small in quantum mechanics. That's what we call the string theory. And that theory is still being developed. And it's doing predictions on how black holes work. And we can use that in these simulations to see how they work, how they influence their surrounding. So what we've done with these kind of things is we've made the biggest database there is on how these images of black holes look like, given all the different conditions and given all the different theories that we have, all the different models that we have. Now, the only thing that we need to do is to compare this thing to the actual image, right? That's the way forward. Okay, now, if we want to make images, how do we do that? So now I'm slightly making a transition from science to practical stuff, right? And I'll get back maybe to a little bit of science later. This is the, what we call the electromagnetic spectrum. I found this thing online as I was traveling to Namibia on the plane, and I actually think it's kind of funny because we have these very serious diagrams that explain, so these are all the wavelengths, and in each of the different wavelengths or frequencies and energies, we have different types of radiation. And we have cosmic rays and X-rays on the side of, let's say, the stuff that has really a lot of energy, and then you have the stuff that has much less energy in the telephone regime, the radio regime, with let's say the longer wavelengths. These are stuff with very short wavelengths. Now, X-rays we use in different kind of things, and the funny thing is you have this whole spectrum. And then you see, this is the part, the small part that our eye is sensitive to. This is a small fraction. You just need to realize, because this is a complicated, funny thing, the only thing you need to realize from this is light is an electromagnetic wave, just like radio emission is, right? So the telescope that we're building is sensitive to electromagnetic radiation, just like light, but we can't see it. It's called radio emission. In this regime, in the regime of 30 to 400 gigahertz, so that's, let's say, in wavelengths, millimeters to centimeters. It's in a regime where microwave and toasters work. You can remember that. So, why do we build a telescope like that? And I'm just going to show you a couple of images and pictures on how it works. This is a schematic drawing of a telescope. And our telescope, radio telescope, will look a little bit like this as well. It's actually quite similar when you think about it. But the most important thing is there's a radio wave coming in. And normally, if you would have a radio telescope, you can build them like this. You can also build them from a simple wire. I have telescopes on space missions that look like simple wires. And these wires, what they do, if an electromagnetic wave passes through the wire, then there's a current being produced on that wire. And that current you measure. You translate that into a digital signal and you process it. That's how a radio telescope works. That's what we're doing here as well. We're basically focusing all the electromagnetic radiation, the radio waves, into one single point, and then measuring that, and measuring the currents that they create, measuring the radio waves that are in there, and the frequencies that are in there. So basically, you have the big dish that focuses all the radiation at the secondary mirror, and then there's a hole in the dish where you push the radiation through, and behind that hole, there's a receiver, there's an instrument that takes that radiation and does that translation from an electrical signal to a digital signal. And then you start processing it. And then this part, the processing part, is, I would say, the most complicated part, because how do you get from this into images, right? That's really, really complicated. And I'm not a big expert in that, so I'm not going to tell you how that works, but it's complicated. Now, this is the design of the telescope. So this is, maybe we're getting into John's regime a little bit. I hope that I'm talking about the things that you wanted to talk about as well. This is the design of the dish that we are close to procuring. So we have a supplier from Germany who builds these kind of telescopes, and we have agreed on a price and a design, and this is the design that they made. So the dish size is 14 meters So standing like this, there's a pedestal, of course, it's a little bit higher. So, but this is about the size of the telescopes that we will get. Now, you can break that down because we will not build the whole telescope in Germany and then transport that to Namibia, but we'll do it in different parts. And those big parts are sometimes quite heavy. And that's why we need good vehicles. And if we put the telescope, for instance, at the mountain, and the Hamsberg mountain, that is still a goal of the project, we need a good road because this is kind of heavy and difficult to drive up that road. Just to show you some of the details. So these, this is made, the whole big dish is not one big unit. It's made out of panels that you connect together, and there's a support structure behind it, right? And that support structure is made out of carbon fiber. It's very lightweight. And then you have aluminium inserts where you put it in and you connect the whole thing together. So you can in principle, build the telescope, take it apart again, and put the whole thing in a container and drive it out, apart from, of course, this big thing, right? Now, that big thing, especially the top part, houses some of the most sensitive equipment that we're currently designing. And I just want to show you an image of that design. What you see here is the way that the radio emission, the radiation, is being reflected by mirrors to the places where we have the instruments. And we'll have multiple instruments, as you can see, working at the same time. So we split the light into multiple parts that go into receivers that do different kind of science. And this is quite complicated to do, right? Because you're losing radiation with each of the reflections that you have. So you have to really be careful there that you don't lose too much signal. And it's also quite complicated because it has to fit in this space, right? And this is not everything, because now these mirrors are just floating in air. That's of course not what's going to happen. These are aluminium panels, by the way. They're designed or cut from a CNC machine. It's high. I mean, they have to have a really nice surface for them to work really good. But they cannot be just suspended in air. So you have to really build a whole structure around it. So that's quite complicated. And this is a design that's currently that we are working on in our team, that we're working and trying to get finished by the end of, I think, next year. If I'm looking at Michael, I think so. Yeah. Because also we go back to the timeline later on. For some reason, I was going back to science again because I like it. This is a little animation of, and we have to go back to science again because science will tell you how big is your telescope. Because the telescope in Namibia is a single dish telescope that cannot make this image alone. And that's why I'm going back to science. The telescope that we need to build needs to see the center of our own Milky Way. It also can see the center of the galaxy M87. 1,000 times further away, 1,000 times bigger, has the same angular resolution of the sky. If you do the calculations, what kind of telescope do you need to build? How big is it? In order to see that object, right? Just to have the resolution to see it, you need a telescope that is able, in principle, to see an apple on the moon from Earth. And that telescope is the size of the Earth. So if you make a telescope, one single structure, the size of the Earth, and you do it in the right frequencies, you could see an apple on the moon, right? So that's the resolution that you need. And with that telescope, the size of the Earth, we can actually see the black hole, the two black holes. Now, how does that work? The Earth rotates. We are not building one big telescope. That's not possible, right? What we're doing is we're building a virtual telescope, the size of the Earth, that has the same resolution and that can see the black hole. Now, on the left-hand side, you see the stations that we currently have in our bigger project, the Event Horizon Telescope. There's an international collaboration with many, many people working on that. We're just part of that. What you're seeing is the network as it basically is formed as the Earth rotates. This is seen from a distance from the black hole looking back at Earth. And on the right-hand side, you see the kind of image that you can create depending on how many of those stations are working. And you can see, if you look at this movie for a while, that the more of these stations you have here, the better your image becomes, right? So this is how we do it. This is how we make this thing, right? And you can also see, if you look closely, that every time Africa comes around, there's nothing there, right? When at the same time, Sagittarius A star, the center of our galaxy, comes right overhead here in Namibia. So we can observe it for a very, very long time. So having a telescope in Namibia would actually be very good. Not only because we can see the galaxy, the center of our galaxy for a very long time, but also because you get all these extra connections that we now don't have, right? So adding that telescope is really going to make a difference. Now, I think I explained this already. Oh, not really. Why are we studying our black hole in the center, and why is the telescope in Namibia so important? This could be a question that I could hear you guys think, because we have the image already, right? So what are we doing? This is the big black hole, right? Supermassive black hole, 7 billion times the mass of our sun. This is the black hole in the center of our own galaxy, 4 million times the mass of our sun. So that's quite different. The timescales on which variations happen around the black hole are dependent on the mass of the black hole. The more massive the black hole, the slower stuff moves around. And if it's less massive, stuff moves faster. So typical changes that you see in this supermassive black hole are in the order of days. So if you observe for one night, you are not going to expect your source to be different over that night, right? Changes that we see here in this black hole, also a supermassive black hole, but a little bit smaller, in our own galaxy, happen on timescales of minutes. So every night when we see something, we can expect that the source has changed as well. So during the whole night of observing, the source will have changed. Now, think about this. As a photographer, you want to take a picture of your dog running around. I think this is an example that one of our EHT members came up with. And the dog is running around. And you're using your camera to try to capture it, right? Now, you only get it like standing still if you make like really, really, really fast snapshots, right? So your shutter has to go really, really fast, right? So you have to have many, many, many images. What we're doing now with making the image of our black hole is that we are taking a couple of snapshots, and then Africa comes by and it's dark, right? We have no telescope there, so we cannot observe. So what we see is not the dog in motion, but we see a blur. And that's what we're seeing in this image. So in these images, many of the things that we see could be blurred. So this blob could be the same as that blob. We don't know, because we've been observing for half a night and not on the time scales of minutes. So we don't see it moving. And that's important. And that's important because that will allow us to make these images more detailed. We can even make movies. We can see over a night how it's changing. And then we can compare that to those beautiful animations that I showed. And that will tell us which of the models and the assumptions that we had were correct, right? So doing this, building the telescope in Namibia, will allow you to get this information and will allow you to do the actual science. Which models are correct? What is the fundamental driving force of black holes? How do they work? So that's the most exciting thing. I'm skipping this for a moment and then coming to some practical stuff, because I guess I may have, yeah, Michael is pointing us as he watch. Yeah? If you say go for it. It's on you, John? So what we're doing now, we're getting to more practical stuff. The reason why we are doing this environmental impact assessment here today is because we want to put the telescope First at Farm Göllschau, next to the HES project. And the reason is that we would like to put it at a mountain top, which is higher and better, but we don't have the money yet to make a road up that mountain. I'll show you later, the mountain is Gamsberg. So the first thing we're going to try is to put it at this place, because we can. We have the funding in place, and also we have, let's say, the momentum at this point. We need to keep on going, because we need to spend some of the funding that we have within a certain time frame, and we want to do some of the science within a certain time frame. So this site is very good. It's not as good as the Gamsberg, but we can do most of our science there. So this is the first step that we're going. We have identified the location already. We've talked to the owner of Farm Göllschau. We have a lease contract with him for part of that, part of his land, and we even hope to have the opportunity to collaborate with the HES project, not only in, let's say, in operations and trying to, work things together, have engineering teams available for both of the projects, but also in terms of science. So that, I think that's something that we are exploring and that we are really keen on doing. Now, you can see me point to the Gamsberg mountain, because that's the objective that we really like to have. This was the main goal for the project, and it still remains the main objective. For that, we need funding for the road, so that will take some time, and we're working on that. But and the road needs to be constructed, so this can take a long time. In the meantime, we'll operate the telescope at HES, at Göllschau, sorry, and then later, when this is done, we move it up the mountain. You can ask me, why do you want to do that? Because as project director, I could say, we put it at the Göllschau farm next to HES. You guys do your science. I've done my task, that's it. But there's something extra here. This mountaintop is one of the best mountaintops in the world. It's considered to be one of the best for astronomy in the whole of the world. So putting an infrastructure here, creating a road, will open up this mountaintop for the rest of the world. This Namibian mountaintop will be one of the best sites for astronomy in the world. We will be the first project, but undoubtedly there will be others coming. So you have a huge facility here with international collaborations coming. Will give a huge boost to the country as a whole, to the research that we're doing here at UNAM, but also think about students that are getting trained in these kind of projects. And they don't all have to be astronomers, but they have plenty of opportunities to work as engineers or as data scientists, also within Namibia. So people can get trained through projects like this. So this is potentially one of the biggest treasure troves that Namibia has, in my opinion, and it's something that we want to pursue as a project. Now, very quickly, I'm not sure if this is also what you wanted to show, John, but this is the place at the Göllschau farm. So we have the C26 going to Windhoek in that direction. There's the HES site, where the HES telescope currently is. And then up there, we have a little corner where we want to put our telescope. And I think I have a zoom in of that as well. We selected, oh, sorry, that goes really fast. We selected a site which is a bit higher. Sorry. We selected a site that's a bit higher, but still we don't have a direct line of sight to the HES project, because we can't be polluting, doing light pollutions to HES. And also, we don't want HES to produce radio signals for us. So we're higher up, but still a bit hidden away. I showed you quickly already the timeline of the project. I think the thing to remember is that we want to plan on starting the assembly of the telescope next year at Farm Göllschau. We have an optimistic first light, and the actual commissioning starts then in 28. that's, I mean, timelines, I was talking to my colleague Michael about this. This changes every day, right? So my project manager tells me, Mark, this is not correct anymore. So take this with a grain of salt. This is a planning of a big project, and it's been shifted. I can show you presentations of years ago where this was going to start in 2020 maybe, I don't know. Anyway, so delays are everything. That's quite normal. I'm going to skip a couple of things because are we still doing a planetarium, Sandre? Okay. Yeah. So this is one other thing, other aspect of our project that I want to highlight. And if the weather is good enough, we can go into the planetarium and you can have a look. This is a thing that we started way in the beginning of our project, where we said, okay, if we want this telescope to be an integral part of Namibia, if we want this to be operated and owned by Namibians, then we need to create those people that want to do this. We want to make them enthusiastic. We want to train them and make sure that it's being used and you know that everyone benefits from it. So the start of that training is engaging small young children at schools. So we bought this planetarium, we brought it here, we trained a large group of students. Some of them are here in the audience right now, and I'm really proud of them, because those are the guys and girls that are making this project happen, because right now they are the ones giving the shows. The planetarium has been supported by a couple of companies and banks here in Namibia. It's self-supporting right now. It has reached over, I think, 30,000 visitors, been to all the regions in Namibia just recently, and it has a huge impact. Okay, cool. So we're setting up now. So then you will experience that, and some of you already have experienced that. The beauty of this thing is, I think Lot is in the audience. He will be pointed out in many of the future meetings as the first AMT PhD fellow. But this guy started, and we're getting into pictures already. This guy started as one of the first in the team. He's now done his PhD, and he's now going on to do other kinds of research, and hopefully he will come back. But this is what's happening right now, just from the planetarium. Not even the project itself. It's the promise of the project, but the planetarium that we're currently doing. I'm just showing you a couple of the pictures of our team and what we're doing with the planetarium, and I just want to thank the students here right now of their dedication, and also this guy that's now setting up the planetarium, because this is amazing, right? This is really, it's really gold, and I'm really, really happy with that, and also the support that UNAM is giving that, and I think this is the beauty of our project. Hopefully we'll get the telescope there as well very soon. Thank you very much. Now I need you want to go back to...
Yes, please, but let's have a question session. You've blown us away. I've kind of wondered, yeah, I want some of the stuff that you've been smoking. But... I mean, it kind of, you suddenly, when you think about astronomy, you have to just forget everything that you know here on planet Earth and just open your mind to a whole new spectrum. So thank you very much, Mark, for helping us do that. And I think before we get down to the really boring stuff about, well, digging the hole in the ground and the environmental impact on the site, let's just talk about some of the science if people have got questions. And we'll use the microphone so that people online can hear. Was that a hand going up or not? Yes, sir.
So when do you expect to have the AMT completely set up on the Gamsberg, ready to operate?
On Gamsberg?
Yeah.
I think on Gamsberg, okay, currently we're talking to people in Namibia, government, investors, to see whether we can raise the money. We need about 10 million euros. We have designs for a road up the mountain. We need that money, and And even if, that's going to take, let's say, another maybe 2 years to get it all confirmed. When we have that, we need to find the right companies to build that road and to make it, start planning it. That's going to take another 2, 3, 4 years. We can ask our friends here in the back, but engineering, doing large engineering projects, you run into problems. This is not an easy road. So altogether, maybe 5, 6 years. And then we need to move the telescope. And that's going to take at least a year, taking it apart, bringing it up, and then putting it back together. So maybe in optimistic 6 years from now? Good question. Yes, hang on.
Yeah, I see on your project timeline you have Q2 of 2029, go or no go move. Can you talk to that?
Yeah, the go no move. That was in 2029. That's related to his question, actually. That may have been an optimistic estimate. But if we don't get the funding arranged here in Namibia, and mind you, we as as scientists, we can raise money in all kinds of programs if it's about science. But I cannot raise money to build a road in another country, right? So that's difficult. That's the kind of infrastructure that the country must provide. So that's why we're looking at, together with all our colleagues, getting that funding here in Namibia. If we don't get the funding, so if in the next 2 to 3, 4 years we don't get the funding, then it's over, right? If that doesn't work, then we're not moving, then we're staying there. So that decision can be made in a couple of years.
Move out of Hess, or is it?
It's moving out of Hess and moving to the top of the mountain. So once we have that funding in place for the road and maybe some of the infrastructure as well, what we can do as a project is again go back to our funding agencies and say, okay, we've built this telescope, it's working here, it's doing a very good job, but scientifically it would be even better if it's there on the mountain. Now, we have arranged the road, right? It's being built right now, so then we can ask for money to move the telescope and to build some other infrastructure there. So that go no go is for us also let's say a gate. If it's a go, we need to find more money to make it happen as well. Is that clear? Other questions? Hang on.
2 questions. When you say fully robotic operation, what does that mean? And what was my second question? What is your plan for the data collection? Because last time Michael at a presentation mentioned the terabytes of data being collected on a daily basis. So do you have plans for that from a data storage perspective?
Okay, so fully robotical, what does that mean? It means that we need the minimum of people operating the telescope. So in principle, we could operate it from a distance. Traditionally, back in the days, telescopes would be projects where you would sit behind the telescope, you switch it on, and you start looking through the eyepiece. So those days are gone. Like modern day telescopes, like the Hess telescopes, we have a team of people working there around the clock. Now, it may sound naive, but we think that we can operate telescopes robotically. We have actually built a telescope in Sutherland, in South Africa, and similar telescopes in Chile, optical telescopes, smaller ones that are basically operated robotically. So the telescope starts to work we operate it from a distance, so it starts to work on its own. If there's an issue, we still are dependent on people, but in principle, that could be it. The second question, yes.
So you can drive this thing from your office in Amsterdam? Is that what you're saying?
That's what I'm saying, yeah. Yes, yeah. My office in Nijmegen, my home office in Haarlem, but yeah, or in China, wherever I am. Now the data question, I'm going to hand over to Michael, because maybe he wants to say something about that.
Well, there's well, this is a quite deep question because the different operation modes of the telescope will have very different data rates as well. So for the way that Mark explained of working together with all the other telescopes worldwide, there is, well, I honestly don't know the numbers, but there's many terabytes recorded, and they get literally shipped to very special computers to do all the data together. And there's, as far as I know, currently 2 in the world that do that. One is in Bonn at the Max Planck Institute for Radio Astronomy, and the other one is at the Haystack Observatory near Boston, which is run with the MIT. So and those are really huge data rates, and there's literally crates of hard drives that get shipped. So that's the one side of things, and then the same a little bit more easygoing way, still terabytes talking, but not crates of hard drives, is then when it's operated in a single telescope setup, and there we shall have computing facilities on site, I would say, or locally, because you don't want to send everything through the bottleneck of undersea cables. But I think we still have a few years to figure the details out of that. I think for that I give over to the project planning.
That's nasty. I see another question. Was your question answered with this?
It's normal speed, a data center or
yes.
computers.
Yes. Yeah. Yes. But we need data centers. We need something here in Namibia. Yes. Hello.
Hi, good evening. I would just like to comment and thank the presenters for highlighting the scientific benefits for positioning the AMT in Namibia. But I would also like to hear more about what are the socio-economic benefits for the country. Thank you.
That's a good question. Thanks for that. The best way for me to answer that question is by explaining how we do these things in the Netherlands, for instance. First of all, we use astronomy in the Netherlands a lot to teach other sciences or other topics, because astronomy is like exciting and it speaks to the mind, so people like doing that, like solving problems using astronomy. So that's one thing. So you can use it as a learning tool. Now, the other thing that you have is the kind of projects that we're doing are high-tech projects, and the requirements that we put for all this equipment to work are the highest standards, right? Even with a project like this, we're talking about we sometimes need new solutions. Like I showed you that optical design of that radiation going somewhere, that's a team of highly skilled people that are coming up with a new design. For each telescope, they make a new design. And sometimes they have to come up and solve problems that they haven't had before. So you're pushing the boundaries continuously with astronomy. And that kind of thing has an effect on the companies that are involved in those kind of developments. So in the Netherlands, we have a couple of companies who are involved into this kind of thing, building telescopes or building instrumentation, and they're constantly pushing the limits of their knowledge and constantly coming up with new creative solutions. And they use that for astronomy. It gives them like this beautiful showcase, and then they can use it for anywhere. And if it works for astronomy, it works everywhere, right? So I had this company that helped us building stuff on the moon. Like we have a telescope that is flying behind the moon right now. That company built a carbon fiber antenna unit for us. There's no company in the world that has that kind of antenna. They can push it out, roll it back in. It's 5 meters long, and it's space qualified because it's flying in space already for more than 5 years, right? So that development alone will cost the company normally millions and millions of euros and 10 to 20 years of time. They've done that in only 3 years with a cost of 3 million euros. They didn't even have to pay for that, right? So you're doing technology development that you normally can't do in a very, very fast time with high requirements. And you're using that, they're using that design for other projects again. So you gain from that. So the social impact is that you're training, and not only people, by letting them use the telescope and doing science and learning how to deal with data, write your own software, be part of a project like this, where you engage with people, all those skills that are being trained, but you're also training the companies and pushing their limits. And I think that is the biggest impact that we create. I can also say that there are companies that are helping us create this project, that are making money out of that. I hope they're making money out of that. That's something that is also an effect, but I think the training effect is the biggest one. Oh. We have a question online
Okay,
as well.
sorry, can I just add to that question? If you do a construction project at that scale, of that nature, that, with this crazy physics, because obviously it's a huge incline, those construction workers need to eat something, live somewhere, probably have families that have their kids educated around there if they want to stay together or whatever. So there's a lot of economic activity in supporting laborers that are operating on several-year project of that scale economically. So services would need to be provided at every level. Yeah, but I mean, that's the construction side. I'm not so familiar with the science stuff.
Yeah, I agree with this, but just think, I'm looking at Lot. And Lot is one of the first students that was in our project. If there would not have been our project here, would he have done a PhD? I don't know. Would he have gotten the research position that he currently has? I don't know. There were not that many PhD students, Namibian PhD students. He's the first now, before we came, right? So we've created that. And then look around the room, there are all these other people. There's Hiko sitting there, exactly the same thing. And that's because of the project that we're doing, and mostly now also because of the planetarium that's related to that. But that's the impact that we create already, right? So I remember when I came, I think we had one astronomy student, I think. This was 10 years ago, and I've never seen her or him. And now we have, at least in our planetarium team, we have 20 students. And they're not all doing astronomy. Some are doing other stuff, but most of them are doing astronomy. So that's only because of that. And I'm not saying we need to create astronomers, right? It's about training people, giving them a right skill set to do other things. And in the Netherlands, we have a lot of astronomers working in banking, in oil and gas, you name it, because they're just smart people. This is not a commercial for myself, but Sandre, is there a question online?
Yes, wow, that's very loud. One of the questions online is, are black holes naturally occurring, and what processes cause them to form in the universe? And then a follow-up, and why are we interested in them?
Okay. Yes, they're naturally occurring. So I didn't talk about how black holes were formed, so I'm actually quite happy with this question. Normally black holes that are, let's say, not these supermassive black holes in the center of our galaxies, but black holes that are a couple of times the mass of our sun. These are formed from heavy stars. So when a star is born and it's quite heavy, it has maybe like more than 20 or 50 times the mass of our sun, it will go through its life cycle really, really fast. So heavy stars move faster than light stars. They burn their energy really fast. And at the end stage of their lives, the core of those stars will collapse simply because there's no balance anymore. And the balance in the star is created by the fusion in the star. So in our sun, we are fusing helium, hydrogen to helium. I saw Michael's eye going, what? So that fusion process is creating energy that is basically the push outward that carries the mass of the star. And that's why it's in equilibrium. If that fusion is gone, then the star collapses. Now, in that collapse, what we call a supernova explosion, when we talk about heavy stars, no, come in. in that collapse, a black hole is formed. And that's simply because there's nothing stopping the collapse. There's so much matter that nothing can stop it to really being compressed to an infinitely small point, a black hole. So this is happening throughout our own galaxy and the whole of the universe. We see sometimes these black holes in correlation or in combination with normal stars, and then those black holes, they eat those stars up, and that matter that falls into the black hole gives off radiation, X-ray radiation, which we can see, and we see thousands of these objects in our own galaxy. So we know that these objects exist. Black holes in the center of our own galaxy, they can be created because everything that's heavy falls to the center, right? Basically, we think that they are, getting more and more matter. So black holes fall to the center, they are merged maybe, they attract more matter, they grow and grow and grow over time. And basically in the images that I showed you, we can actually see black holes falling, stars disappearing into the black hole. So we know that the black hole is eating up stars in the center of our own galaxy. So this is all naturally occurring. Now, why do we even look at this? Why do we need to understand this? This is a fundamental question. Why are we curious? Why do we do science? Why do we want to know if the Earth is round or flat? That's a thing that we need as humans, we need to investigate this, I think. And the other thing is, if we understand how physics works in black holes, I think I explained that we're working on the models, doing predictions of how it would look like, and then we're comparing that with the actual thing. So we hope at some point we get a better grip of what is the physics that's driving the black holes, because we don't have that physics right now. But if we get that, then there's another very interesting thing that is all the way at the beginning of our universe. Just before the Big Bang, or actually during the Big Bang, all the matter in the universe and all the energy was confined in this very, very small space, infinitely small, just like in the black hole. So to understand maybe how that beginning of the universe was formed, how was it formed and why did it go like that, we need to understand how physics works in those small regimes with lots of mass. So we need to understand how black hole works to understand how the universe works. So that's why we need to study it. I hope that's a good answer online.
Okay, I think we're done with... Oh, Sandra, you have another one? Oh, there's one more online. Okay, go for it. Into the microphone. Once it's established, will it be time limited, or how long does it carry on for?
Yeah. Okay, it's a good question. I think we've gotten all the funds together to build a telescope and then operate it for at least 5 years. But telescopes like this can go on for 10, 20, 30 years. Right, so look at how long HESS is already being operating, and I was there with Tony a couple of weeks ago, and I asked him this question: is it still functioning okay? Is it? I mean, those guys are doing maintenance on the telescope, obviously, but it's aging, and Tony and the other engineers tell me it's perfect, right? It's still working. It's been there for more than 20 years, and it's still doing its job. So projects like this can go on for a very long time, provided there's funding to keep them running, right? Because you need maintenance, you need people, and you need people to use it as well.
How long was the one in Chile? How long was it active?
Which one?
The one that's collapsed.
Oh, I don't remember. I don't know. Yeah, Arecibo is collapsed, but that's not in Chile. That's in Mexico, but that's collapsed under its own weight. You shouldn't build things too big.
And tell me, just give me the price of the estimate for the road.
The new road that we want to build up the mountain is about 10 million euros.
Now, would a helicopter not be cheaper?
You're the first to ask that question. No.
Are expensive, I know that.
Yeah.
But I mean, weight-wise, it's no problem.
Yes. Okay. The answer is no. And there's two things. It's not a permanent solution, right? Because we can use a helicopter once, but then the next project needs to use a helicopter. If we have to bring other stuff up, we need to use a helicopter. So you're constantly flying up and down this mountain, so that's not going to work, because these helicopters are extremely expensive.
It's not a one-time.
Yes, no, it's not a one-time. But we're building an infrastructure that needs to be accessible, right? And the other thing is, these components are extremely heavy. And if you fly this high, then it's difficult for those helicopters to do that. So we've talked to experts about this, and they said, maybe it's possible, but if it fails, you don't want to be in the helicopter, right?
And there's an engineer here who wants to give us an engineering answer to that.
Yeah. Thanks, Richard from Lethon. I was previously tasked by the university to investigate all avenues, a road, a cable car, and of course a helicopter. The helicopter is sort of an option, but it's dependent on time. You can't fly, or you wouldn't be able to fly coming September to March, April. It's just too hot, and the air is too thin, especially in the area where we are. So, and then the next problem is there's sort of only one helicopter in the world that can carry 20 tons. So getting it here, and it's not in their interest to help you. So you can't get to those people that have that helicopter, and it's a Russian helicopter on top of it. So it can be done. What the telescope is so sensitive, it can't be broken down into smaller parts, because then it becomes unstable and it's got vibrations and all of that. That's why some of those parts are that big. So the helicopter would have been nice, but it doesn't work. The cable car would be the next option, but you have to get to the cable to the top somehow, and you need another helicopter. So it's just like a vicious circle, and you end up then with a road which is perhaps not the best, but it gives you all your access. Once it's built, you can do multiple things on the table deck once you are there. So the construction is a bit of a challenge, but thereafter you are free for whatever you want to do.
Okay. All right. Are we good with the background? I really enjoyed that thing. I actually haven't understood all this excitement about this black hole until now. So thank you, Mark. It gives us a really good background. So now we're down to the really mundane stuff about how much concrete do we need, etc. But okay, so now we're just going to go into the details of what actually is going to happen on the ground, and if there are any environmental concerns, this is the other chance to raise them. So this map shows, the inset shows where we are on the map. So there's Windhoek, and that's the main north-south B1 going that way. So the place we're actually building this thing is Farm Göllschau, which is on the C26 road going southwest out towards Gamsberg. Gamsberg is there. Okay, so this is the C26 coming down here, and it does a kind of a dog leg here and starts driving towards the west, towards the coast. And just before you get to that turn in the road, there's an inconspicuous signpost going to the Hess site there, and then the AMT, our telescope, will be a little bit distance away from that. So it'll be on its own road, its own little access road coming off of the C26. And there's a little bit of an upgrade to the road which is required there. At the site itself, we've already seen some of this from Mark's better pictures, but this just shows the Farm Göllschau. That's the boundary of the farm. Sorry, it goes all the way across here as well. The Hess site, they've got quite a large chunk of the farm, which they have got an agreement with the landowner. So the Hess telescope, there's 5 structures all based there. And the AMT is going to be positioned roughly within this yellow square. I don't know if that site has been precisely identified yet. But what's important just in terms of impacts, when we had this meeting at the Göllschau farmhouse just 3 weeks ago to ask local farmers about their concerns, Hess was the first crowd to stand up and say, well, actually, there's a potential conflict here, because if any light shines from what's happening here onto their telescope while they are busy at night, it can really badly damage the Hess telescope. So it's an absolute thing which they cannot risk happening. No light must ever shine on their dishes when they are working at night. So there's going to be a gate to actually stop anyone moving up this little gravel road, 2 gates to actually prevent anyone getting over the crest of that little hill and shining their lights towards the Hess telescope. So that was something which is an important consideration for the sighting of the scope. Well, not so much the AMT itself, but the road towards the scope, and that has been, I think, easily resolved in a discussion with the people involved in the AMT. Okay, so these are very simplified diagrams of kind of what's to be expected on the site. It's quite small, 80 by 80 meters, so that's less than 1 hectare in size. In area. There'll be a solar array, a little photovoltaic set to actually generate battery power to drive this thing. These little individual buildings here, these are different buildings which are there. There's a control and IT room, there's a meeting room, there's a bit of accommodation, there's a workshop, there's battery storage and a generator. So it's a fairly simple matter on the ground and really a tiny, tiny footprint. We have had an input from the botanical crowd who were all saying, well, are we sure we aren't going to be squashing any indigenous or plants? Obviously there'll be some clearing of the area, but in fact this is the Kommershochland, which is a fairly homogeneous biome over a large area. And from the work that I've been able to do, just very kind of superficially looking at what plants occur there on site, there's nothing which is so range restricted that it would need to influence precisely where the AMT gets situated. I can just mention that on the Gamsberg, that was a very different issue, where there is a plant there which grows only on top of the Gamsberg, this Euryops walterorum. And we had a botanist with us when we did the EIA for that project, when this thing was started 7 years ago. And the situation of the AMT was actually shifted to make it be positioned in a place where there was almost no Euryops to actually cater for that range-restricted plant up there. The construction period, if they do start after the rainy season next year, then there'll be about 3 months of just doing these basic things to actually construct the slab. This, as you can imagine from what Mark has described, this thing which is looking up at the sky cannot move 0.5 millimeter, otherwise all of your calculations are buggered. so this thing has to have a really solid foundation, and all of that will be created. There'll be some accommodation will be erected, those little buildings that I talked about, so that'll all be put up in the first 3 months. So there's a fairly short space of time when there's a number of workers on site. It's basically just a kind of civil construction exercise, and the workers, about a team of approximately 10 people, will be housed at the Farmers Association Hall. From then on, once all of that foundation and slab is in place, then the assembly, the delivery of the parts, they get brought to site, probably via coming in from the coast at Walvis Bay, coming to Windhoek on a tar road, and going out on the C26, and construction and assembly of the AMT. This is being done by, I believe, a company in Germany. Is it still MTEX? Have I got the right picture here? This is taken off of the web. So that's what they do. They build these telescopes. And that's a very small team of people who are stationed there on site for about a year. They are putting this thing together in the nice way that Mark showed, with all of those, all of the scaffolding and whatnot to keep it all in place. Okay. So the track, that short track, about 4 kilometers of distance, needs to be upgraded so that it can take those heavy loads. Fairly standard construction activities, a mobile crane for actually maneuvering these things and shifting them into place. You might ask, so where's the water coming from for all this concrete slab? The engineers have announced that it's probably easiest, you've got better control over the quality of the concrete if you mix it here in Windhoek and then haul it. What is the distance? It's just less than 100 kilometers to site. So it's a bit of a long distance to haul, but it seems to be worth it to do it that way. So there's not going to be any spike in demand from the local groundwater. The farmers were concerned, well, groundwater is very limited here anywhere. How are they going to have enough water? But actually, most of the water goes into that construction of the slab, and that will be done here in Windhoek. So that deals with that issue, and then ongoing. The people that you have there on site, as Mark had said, it's not going to be many people. It might not be occupied for actually months at a time. So it's very, very low water consumption to actually keep this thing going. The power for the site, there'll be mobile generators. There'll be solar power on site, as I explained, and a power bank. And the machine is actually designed to be operated from that power bank entirely. There was talk about having a separate power line on the farm as a backup, but I'm not sure if you've arrived at a final decision on that. Richard, is that still something which is to be decided about the power line? Sorry, I'm putting you on the spot here. Just into the mic, please.
If the telescope is low on power spikes, then we probably get away without a power supply, or let's call it NAM power.
So there's no complication about having an extra power line going to the site there. Okay, and as I mentioned just now, transport of the telescope coming in from the coast and getting to the site via Windhoek. So I kind of gathered there are certain times of the year when all your attention is focused, everything has to be coordinated, you're kind of looking at, you're trying to get all your telescopes to look into that black hole right there, so it's kind of frenzied activity, but only for a short space of time. And then, as we heard, operated remotely. So in fact, you don't need to have many people, or maybe any people actually on site. And then there'll be occasional use by scientists from UNAM and international scientists, but it's not expected to have any permanent presence on site. And how does this all get secured? Well, there's just simply an electric fence around the perimeter, and possibly I'm not quite sure what more than that is required, but it's very straightforward that way. Okay, so the benefits we've talked about, Mark has talked about socioeconomic benefits kind of worldwide, and for Namibia, the recognition that Namibia will gain. And it's nice to hear you say about, well, Gamsberg is like the best spot in the world. I thought, yes, ha! And also it kind of begs the question, why haven't we done this 40 years ago? The road. The road was the obstacle, okay? And so there seems to be a plan to get an entirely different route up onto the plateau from what exists at the moment, okay? And so there are various academic and kind of social benefits, and I think that whole thing of upskilling people, even if we don't train people, even if people who are trained in astronomy don't actually stay in astronomy, they just develop a whole skills base, and it's and that can really help the country generally. So now coming to the negative impacts, which is always what my main role is to identify those things that might happen down the line, the consequences we didn't think of, and maybe there are problems with this thing for the local farmers or for his telescope, as I've described. So that's the view from the top of that hill, which I said you can't take your headlights over that hill because then you'd shine onto their dish, which is looking up at the sky at night. So already the concern was raised, and we've had communication from the Max Planck Institute saying that some sort of measure has to be implemented to make it absolutely impossible for anybody to come over this rise and shine their lights towards Hess at night. So that seems to have been resolved. So that was something fairly simple to sort out. There's a short period of construction when you have people who are brought into the area, staying there, and that always raises the possibility of accidental fires and any sort of illegal activity of people hanging around and doing things in the surrounding farming area. These are relatively small impacts and are kind of manageable as long as you put in the right measures. So disturbance to the overall area, there's going to be a lot more traffic on that road. An intense period of all of these pieces are being delivered along that gravel road. Not only more traffic, but heavier loads on those trucks. And so that road is going to get really badly corrugated from all of that activity. So that will probably need some extra scraping, some sort of arrangement with the roads authority to actually keep that road in better, in decent condition for the 3 or 6 months of that intensive traffic. Sorry, I'm jumping around here. I went to number 2 first, and then we discussed that. But these are things where it's an inconvenience, but it's nowhere near a fatal flaw for the project. It's things which you can manage and introduce the measures to actually make those inconveniences a little bit more palatable. Water for construction operations, I said it seems to be a very small consumption overall, so I don't think that is going to be a limiting factor. Clearing of vegetation on site, as I mentioned, we have had this communication from the National Botanical Research Institute, NBRI, talking about the lack of a botanical study, firstly, which wasn't mentioned in the background information document, so I'm assured them that is happening. And it's a kind of low key, it doesn't have to be, we don't have to employ a botanist to go and do a long intensive site visit there. It's a tiny area, and that area is homogeneous over a large space all around it. So the risks so far that we've identified are totally insignificant. And then archaeological risks, as I say, it's a mandatory thing that you have to get clearance from the National Heritage Council, and if there's any archaeological remnants in that area. So that is being done. This all seems very, very mundane compared to what Mark was telling us about. Just anyway, now your thing isn't listening to me. It doesn't want to, let me see. You've kind of got to come and give your magic fingerprint here, Mark. Okay, there we are. So yeah, that is it. Thank you. So that's all we've identified so far. It's a fairly straightforward project. The EIA is not a complicated issue. I think the environmental clearance certificate is just a matter of going through those steps and making sure that we put the right mitigations in place. Okay, so The public consultation phase has already been running for about 5 weeks since we actually put the first advertisements out in the newspapers. We had a public meeting at Göllschau with some of the local people. People came from one of the neighboring farms, well, a few of the neighboring farms. So we have had discussions with people on the ground there, and we're trying to wrap things up. So if anybody does want to send us comments, please, we're asking for a deadline, and that is tomorrow. If you think that is unreasonable, you want to kind of ruminate over, well, what other impacts might there be, then we can relax that. But we are in the process of compiling that scoping report and putting our thoughts down to assessing those various things and making sure the mitigations are in the environmental management plan, which is what the construction team is. It's a kind of set of instructions for the construction team that they must abide by. So we've been gathering the feedback from HES and the NBRI and so on, and compiled them into the scoping report. That will get circulated once we have finalized the scoping report to people, and that will fall over the Christmas period. We aren't doing this intentionally to try and bypass any input which people want to make, so we'll extend that into January, so that people have got a chance to look at that report and make sure the issues are being adequately addressed. Then the final scoping report gets submitted to the ministry, and hopefully it's a fairly straightforward process. It seems to be straightforward, but that doesn't mean it's quick. So the ministry takes a bit of time. 3 months is kind of the minimum at the moment of how long they take to issue an environmental clearance certificate. So there's a bit of a time squeeze now to make sure we get that ECC, so that we don't hold up the beginning of the construction, the first things that must begin to happen on site in April or May next year. So that's it, and that's where you can send your concerns to, unless you want to raise them now. And I didn't really give anybody a chance to say, to say if they have got concerns. Is there anything that anybody wants to raise? Any issues which we haven't considered, or want to? It's not quite that final, but okay. But I don't see any hands up. But if you do want to send any comments, please do so. Remember, my name has got 2 T's at the end. If you leave out the second T, well, that email will go to the moon. So, and then there's my consultant, Henriette Potgieter. Those are the addresses you can send your concerns to. Okay, that kind of wraps it up from our side. I think we can say thanks to everyone for your participation. Thanks for the questions. Thanks to Mark and the team for this inspiration. It really is inspirational stuff, this. And I have to confess that I'm very much in favor of this project. An EAP, an environmental assessment practitioner, is supposed to be completely neutral. Well, I can't help getting excited about this thing. So anyway, are we done? Okay, thanks and cheers. There are some drinks.
And there's an option now to go into the planetarium, I think. It's still outside. If you want to do that, if you have not done that now, is it possible? Yes? Zandre can take us.
So if anyone wants to join, let's maybe do this. Who wants to potentially join a planetarium show? Okay, so you guys are all welcome to stand up and move outside. The team's ready. They're going to give you a quick briefing and get you in, and then we'll do a show for you, hopefully before the rain comes.
How many minutes is it?
So a show itself, on average, our normal show length is 40 minutes, but it's interactive, right? So you can make it 5 minutes, you can make it an hour and 50 minutes. It really depends on your curiosity, how much time you have, how many questions you want to ask, and where you want to travel to in space. It's not a film. It's real data programmed into the planetarium with real smart Namibians who are studied in astrophysics, like Lot and the gang, and they will literally fly you, and not just to the moon and back, but even further. So you're welcome to go on a tour of the universe. I just hope you brought your passport, because obviously if you want to go outside of the country, you need that. But we'll bring you safely back, don't worry.
Okay, thank you, thank you, thank you. There are some drinks at the back. We're asking for a small donation, but if you want to just have a drink with you and chat with any of the team here, you're welcome to do so. We can stick around while all of that happens. Okay.
Yeah, thanks, John, again. Let me just briefly conclude in that I'm switching my hats, now putting on the hat of the chair of the Namibia Scientific Society. It was a pleasure of having you here. You might have seen those books at the edge of the room. You're welcome to take along, and you're also welcome to leave some of these notes from your purses behind in those donation boxes as you see fit. I must admit, most of those books that are currently here on offer to take along are in German, so they might not be of interest to everyone, but just browse around, whatever might pique your interest. At the bar, it's the same principle. You're welcome to have a drink with us, stay a little longer, but you're also very welcome to leave behind what you deem might be a good idea. So with that, thank you. Thanks, John, and let's have a great night. Good night. Bye.